All right, so we've talked about the cycle GAN, right? Going from a horse to a zebra and going from a zebra to a horse. Some researchers noticed some interesting points about these cycle GANs. So let's look and see if we can look at this example. So here, this was an example where we would take aerial photographs and create generated maps like you might see in Google Maps. And so we used a cycle GAN was used for this. So you could go from an aerial photograph to a generated map, and a generated map back to an associated aerial photograph. And all, again, we really needed with that were examples of real aerial photographs and examples of real, not necessarily related, generated maps. What is interesting is the learned generators could learn to go from this aerial photograph to this generated map. And then, from the generated map, they could go back to an aerial photo. What is interesting is the amount of detail and how good the aerial reconstruction was. So for instance, if we look at this area here with the white, there were all these dots which are part of, I think, the top of the building. Here, they're not present. Okay, we have no such dots. And yet, when we went back to the aerial reconstruction, they were back again. How can that be? Or in the case of the horse, you'd see what happened is the zebra generator would generate this zebra, and then the horse generator from that zebra generator would generate a horse that looks very close to this. That part doesn't seem surprising, but keep in mind there are lots of different horses. A lot of horses of different colors, right? There are white horses and black stallions and brown horses and reddish kind of horses and so on. How is it that we know how the zebra generator came up black and white. Zebras are black and white, right? But how did the zebra generator know to come back to a brown horse instead of a black horse or a white horse? If you just look at a zebra image in isolation and say, create me a horse from that, you wouldn't know what color to create. Yet, it turns out this horse generator would generate horses of the right color, such that if we took the zebra generator and generated a zebra and then went back from this image, we would generate a horse of a right color. If we went from a white horse to a zebra, then when we created the horse from that zebra, it had come up with a white horse. How the heck is that? The cycle GANs, it turns out, have invented steganography. So steganography, steg from the Greek, hidden words, okay, hidden writing. So cryptography is this idea of making something that no one else can understand. But when you look at cryptographic output, you know there's some hidden message there. In steganography, the idea is to have a hidden message, but also hide it such that it's not even clear there is a hidden message. Okay, so for example, we might have a letter that someone writes that says, let's say, hello, Ernest. Looking past my excitement, Neil. So this is kind of an odd sort of message, but that's my message. Well, I have hidden in here a message, help me. Okay, so I sent this to someone and they can now find in there some hidden message. So steganography is hidden messages. Right, the etymology, again, graphy is writing, so often this was in terms of hidden messages inside writing, but you can also hide messages inside images. Let me give you an example. Let's say you've got an image. So we've got RGB values in here, right? So in fact, let's just make this grayscale for simplicity. So we've got some values. This is, let's say, a 0. These are going to be numbers between 0 and 255. So a 0 and a 3 and a 27 and a 29. And I'm going to just make this 4 by 4 actually, so it's not really going to represent this image. And a 128 and a 252, and a 3, and a 65, and numbers like that. Well, if I make slight changes to these values, we're not going to be able to perceive them. So let's say I allow myself to adjust any of these values by at most 1. That shouldn't be perceptible. So I'm going to look at every pixel, and I'm going to come up with a code. So I'm going to try and encode 1 bit in here. So what I'm going to say is that on the output, if this is a even value, right, its parity is 0, then that's going to mean a bit 0. And if the parity is 1, that's going to mean the bit is 1. So let's say this is my hidden message. My hidden message is in binary. So my hidden message is 0, 1, 1, 0, 1, 1, 1, 0. Okay, that's what I'm trying to hide into this image. And so I am going to go through and apply this to each of these values. So for a 0 bit, I'm going to just ensure that the outgoing bit is even. So I'm going to leave 0 alone. For a 1 bit, I want to make sure that the output bit is odd. So actually, I leave 3 alone too. 27, I leave alone. And 29, I'm going to change to either 30 or 28. And then a 1 for 128, I'm going to make 127, okay, because I could go up or down. 252 should be a 1, I'll make it 251. 3 should be odd, so I'll make it a 3, and 65 should be even, so I'll make it a 66. And now how do I read my hidden message out of there? I just go through bit by bit. I say if it's even, it's a 0, and if it's odd, it's a 1. So this is going to be 0 is even, 3 is odd, 27 is odd, 30 is even, 127 is odd, 251 is odd, 3 is odd, and 66 is even. So notice I have retrieved my hidden message from my image, and yet the image is only different by at most plus or minus 1 of each individual pixel value from the original. So something that I wouldn't be able to see visually. This is the idea of steganography. And that is what our CycleGAN is actually doing in some way. When the CycleGAN is being trained, if it has a brown horse and it goes to a zebra and it comes back to a red horse, it's going to get a lot of loss, right? Because everywhere there's a brown pixel and instead is a red pixel, it's going to have error. And so those will add up, and that means squared error. What has happened is a coevolution between GZ and GH, and they come to some sort of agreement. So GZ, when it takes the horse image and outputs a zebra image, it outputs a zebra image with the horse color hidden in the image. And then when we go through G sub H and it extracts the hidden horse color and uses that when it comes out with the horse. So it comes out with a horse of a correct color. And no one explicitly told the GANs to do this, right? The G sub H or G sub Z. Instead, this just has to do with the loss function. And our loss function was 1, fool the discriminator. And both of these are still fooling the discriminator, okay? It's not like we created a zebra with a big label on top of it that said brown, right? And then the discriminator might be confused and say, you know, we don't have, if I see a zebra with the big words brown on top of it, I don't ever see those in real life. And so therefore it would fail. So it's not going to be doing anything to the zebra that might affect how good the discriminator is at being fooled. So it makes the zebra look really zebra realistic. It makes the background look pretty realistic as well, because remember that we are doing this mean squared error between these. And again, the mean squared error is going to get a penalty if the background is very different. And it's going to also get a penalty if the horse itself is very different. So we know we're going to have a horse in the same location as the original horse, but we want actually all the features and everything and the colors and so on to match. And so the generators learn, the best way to do that is I'm going to get penalized if I have these large areas that are wrong, like these browns. So I'm going to store that information in some sort of low bits in the image. Why in the low bits? So that I get a low mean squared error. Right? Because if I have 1 bit difference in 1 pixel, that's a very low error. And if I can somehow use a few of those low bits and then minimize my loss from having my color wrong, I'll do that. So that's an interesting example of a neural network. I'm not going to say being smarter than you think, but certainly learning something different, you would think, and generating something different than you would think. This idea of steganography and hiding information to be used in later reconstruction is not only something that wasn't intended, it wasn't even something that was expected. And to begin with, before this was looked into, it was sort of surprising at how good this round trip could be, right? How it could actually do such a good job of coming back up with some image that looks so close to the original horse. And I'm not saying it's necessarily horse color in here, that it's specifically choosing. It's all sorts of things that might be specific to this horse. So it's enough information, basically, such that we have a zebra, and we have the background, and then we add in some additional hidden information to be able to try and reconstruct as close to pixel for pixel as we started with.